What if you could build quantum error correcting codes like Legos in a modular, intuitive, visual way, but fully grounded in math? Hi, I'm Balint Patu, a PhD student at Duke University working on quantum error correction. I'm very excited today to announce PlanqTN, a set of open source tools that helps researchers to learn, explore, and share tensor network QEC codes using the quantum Lego formalism. When I first saw this paper by Charles Tao and Brad Leckie, I got very excited. This formalism allows to build from smaller codes like the 422 code here, larger codes like the Steam code, in a way that generalizes code concatenation. It's visual and it allows through this thing called operator pushing to track logical operators as well in the resulting tensor network, and it allows for faster weight enumerator calculations as well. So I'm very excited to announce PlanqTN, the first release that was released yesterday to the public, which gives, it's an implementation of Quantum Lego as a Python library and as well as a visual interactive studio on planqtn.com. So let me show you how it works. I'm going to navigate to planqtn.com, open up the canvas, open up the building blocks panel, and then I'm going to build the Steam code out of two 603 tensors, just like we saw it on the paper. So I drag the 603 tensor here. I can actually see the stabilizer generators. These are the regular physical lag stabilizer generators. And because it's an encoding tensor, we can see the logical operators pushed as well, which is just the stabilizer on the stabilizer state of the encoding tensor. So we can see the stabilizers for that state, which are going to be basically the logical operators. Excellent. Let's clone this by shift click and connect the logical legs like we saw it in the paper. I select the new tensor network and calculate the parity check matrix for that. I can sort it by X and Z types. And so if we see that the stabilizer generators are basically self-dual, and that the state is an 8-legged tensor. It's a stabilizer state. This is indeed the encoding tensor for the Steam code. Steam code encoding tensor. But I would like to see and calculate the distance of the subspace. So we know that this is very symmetric state, so I can pick any of the leg. I'm going to drop the identity stopper, which is a small extension of the quantum Lego language that allows you to create subspace tensor networks. So we can see that this is a 7-1 CSS stabilizer subspace. I can also do the CSS sort here to X and Z stabilizer generators. And I don't see the distance here. Distance calculation in general is expensive, so we don't do that automatically. But there are a couple of options how you can do that. Using the Steam code stabilizer subspace. So one way to do that is by calculating the weight enumerator polynomial. This needs a login, so I'm going to log in. But you can do a lot of things without logging in. If you don't want to run a backend calculation on the cloud, you're going to be good. And you can export things to Python, to NumPy, which I'm going to show in a second. But let's log in. I'm going to sign in with GitHub. This is the first time authorization page that you will see. And it goes back here. And then now the weight enumerator calculation button is enabled. So I'm going to hit calculate. And this is going to kick off a backend job on Google Cloud Run, calculate the scalar weight enumerator. In the meantime, I'm going to spin up a local kernel as well, because it is possible to run a local kernel. On the cloud kernel, jobs are limited. Let me just kick this off. So first of all, I need to install PlanqTN CLI, which is a tool to manage the kernel, the runtime kernel. And for developers, it's a tool to manage, it's the developer experience entry point. So HTN is the name of the tool because H is the Planck constant, and then TN is for tensor network, so that's why it's PlanqTN. And then HTN kernel start will kick off a bunch of components using Docker to spin up the local version of the job execution framework. So you can see that this component, which is the database, and then the runtime environment, which is using Kubernetes, is going to slowly start up. In the meantime, our weight enumerator has been calculated in the cloud, and we can see that it is indeed distance 3. Another way to see that this is distance 3 is by exporting the stabilizer generators or the parity check matrix as a qdist RND set of instructions. So as soon as I get my CLI back, and we can see that the containers finished setting up, I can open a gap CLI and REPL, and then paste the copied code. So this is the symplectic representation of the, well, actually not symplectic, this is the gap qdist RND specific representation of the operators. And so I hit enter and I see that the distance is 3. Woohoo! Excellent. So let's run one calculation on this local runtime just to demonstrate it. So I'm going to switch to the local runtime. So I have to run this kernel status command to get to make sure that everything is running, and then I get the connection details. So from my browser, the UI can actually switch to the local runtime, and I can kick off a calculation using now this local environment. So the local environment has no limitations like the 5-minute limit or the 1 GB limit. Everything is just limited by your computer's needs and time. So if I start up the monitor here, this will monitor the Kubernetes cluster, and then we can see that the container is already creating and it's running. So it should talk back to the UI in a second. And then we're going to see a weight enumerator that has 2 open lags. So we see all these poly operators on these 2 open lags, and the weight enumerator, tensor weight enumerator entries for those polys on the open lags. Fantastic. So now we saw how you can determine the distance and calculate weight enumerators. So the weight enumerator calculation is an expensive one, but it is still faster than doing a brute force one. And then for that, I would like to show you in the documentation an example. So the documentation is accessible using this link, or for a given component, you will find these little question mark items that will bring you to the right section of the help. So the Python API, Tensor Network Contraction, shows off this cool comparison of rotated surface code, weight enumerator calculation for distance 3 and distance 5, using the tensor network method from Quantum Lego, or doing a brute force calculation. So for that, I'm going to create a virtual environment and install PlanqTN. And so while this installs, I can show you that the roadmap contains a lot of items, and this is a continuously evolving list. And we really would like to see more ideas and contributors. Plankton is in its very early days. So if this is exciting to you, please get in touch and open an issue, send us your ideas, your feedback, or if you find bugs, and become a contributor. Excellent, almost there. And then, so now I can start Python, copy paste this code in, and then we'll see that for the distance recalculation, using the tensor network contraction, it took 0.03 seconds. With the brute force, we had to go through all the 2 to the 8 generators and 2 to the 8 stabilizers and then check the weights for them. We get the same result, but it was much slower. If I do this for distance 5, the situation is going to be more dramatic. So we saw that the distance 3 was ran in 0.1 seconds, and for distance, and then the brute force one, 2 to the 24 generators are a lot, and so this would take an hour currently on my computer to execute. So I'm just going to cancel that. And that's it for today. I really hope that you're gonna explore and look at all the features and learn something and contribute to our project. Thank you very much for listening, and I hope to see you out there in conferences and on GitHub.